right, in our last chapter, chapter 12, we're going to do a few sections and talk about exponential functions. So we've talked in the past about linear functions, right, lines, and we've also talked about quadratic functions. Remember parabolas? The last kind of function we're going to talk about is what we call exponential functions. Now, an exponential function is when we have a base and an exponent, but our base is always going to be a numeric value other than 1, and our variable is going to be up in our exponent. So for example, if I give you the equation f of x equals 2 to the x power, that's an example of an exponential function. My base is 2 and my exponent is the variable x. The first thing we're going to do with exponential functions is we're going to graph them so we can figure out what the graphs of these look like. They're not lines, they're not parabolas. Let's figure out what they look like. And if we don't know what a graph looks like, remember we can always do a table of values, pick x's, plug them in and find the y's, plot a bunch of points, and then look to see if we can figure out the pattern. So that's what we're going to do on the first two examples. So look at example number 1 with me. Again, I have f of x equals 2 to the x power, and we want to go ahead and graph. So what I've done over to the side is I've made a table of values. I've just picked all different types of x values so that I can plug them in, I can evaluate, and I can figure out what the y value is. So I have a whole bunch of different ordered pairs. I went from -10 all the way to +10, picking -5, -3, -1, 0, 1, 2, 5, and 10. So here we go. We're going to take and evaluate all of those. I started with f of 0. So I'm going to plug in 0 wherever I see an x, and we know that 2 to the 0, anything to the 0, is 1. I'm going to plug in 1 now. 2 to the first power is 2. Let's plug in 3. 2 cubed is 8. I'm going to plug in 5. 2 to the fifth power. 2 times 2 times 2 times 2 times 2 is 32. So I'm just plugging these values in to my function so I can figure out what the output is, the y value. I'm also going to do 10, and I ended up getting 1024. Now let's do the negative values. Let's do f of -1, f of -3, and f of -5. Now be careful. When I plug in -1, I end up getting 2 to the -1 power. We know in math that that doesn't really make any sense until that exponent is positive. So remember how to make those exponents positive. Remember, we can take that 2 to the -1, drop it down to our denominator, and make it 2 to the +1. It turns into then 1 over 2, 1/2, or 0.5. Let's do the same thing for -3. I have 2 to the -3 power. Let's make it positive by dropping it down. I have 1 over 2 cubed, which is really 1/8, or as a decimal, it's 0.125. Do the same thing for -5, and the same thing for -10. Now let's go ahead, put them in our chart, and let's graph these ordered pairs. So it looks like I have a couple of different points here. I have the point 0, 1, 0, 1. I have the point 1, 2. I have the point 3, 8. I have the point 5, whoa, 32 is going to be way off my chart. And I have the point 10, 1024, that's going to be really off of my chart. But imagine that there's points way up here to the top at 5, 32 and 10, 1024. Now let's look on the other side. If I have -1, 0.5, that's -1 and about a halvesy, right? Then I have -3, 1.25, -3, 0.125, I should have said, so just a little bit over 0. Then I have -5, 0.03, that's really close to 0. And then I have -10, 0.00098, that's really close to 0. You notice as we go more negative on the x, my graph kind of approaches 0, right? And it's going to keep doing that and go close, really close to 0, get smaller. But as I approach positive infinity, as my x gets bigger and bigger and bigger and bigger, what happens with my graph? Well, yeah, my graph kind of shoots up really quickly, right? What this is called is exponential growth. Okay, so I have a graph that kind of looks like this and it goes really quickly up. You notice that when I did 2 cubed, I got 8, but 2 to the 5th power is 32, and 2 to the 10th power is really big, 1024. So the bigger my x, the extremely bigger my y value gets. Exponential growth. Let's go ahead and do another one in this video, and I want you to compare the equation with its graph. So look at example number 1 versus example number 2. What do you notice that's the same, or maybe what do you notice that's different? Well, I noticed that in example 1 and 2, they were both exponential functions. They both had a base, and the exponent was a variable. But my base on example number 1 was a whole number, 2. The base on example number 2 is a fraction. Let's see if that makes a difference in my graph. So I'm going to do the same thing. I picked a whole bunch of x values. I'm going to plug them in and find my y values. Why don't you do that? Why don't you pause the video, plug in all of these different x values into your function, evaluate them, and find the y value that corresponds, and then come back and let's make sure we have the same points before we go to graph. All right, when I plugged in x equals 0, I have 1/2 to the 0 power. I know that anything to the 0 power is 1. If I plugged in 1 for my exponent or my x, I end up getting 1/2 to the first power, which is just 1/2 or 0.5. If I plugged in 3, I have 1/2 cubed. That's a half times a half times a half, or can I say 1/8 or 0.125. If I have 1/2 to the 5th power, that's really 1 over 32 or 0.03. And 1/2 to the 10th power is really 1 over 1024. That's 0.00098. Those numbers look familiar, don't they? All right, let's look what happens when we go in the negatives. If I have 1/2 raised to the -1 power, remember negative exponents don't make sense to us, right? So we have to make them positive. And remember, if our base is a fraction and we want to make our exponents positive, we can simply do the reciprocal, and then my exponent changes to a +1. So I can put the numerator down to the denominator and the denominator up to the numerator, and that changes my exponent to a +1. So then really, I have 2 over 1 to the first power, or 2 to the first power, which is just 2. I'm going to do the same thing with my -3. I'm going to make it positive first by moving my numerator down and my denominator up, making that exponent positive, and end up getting 2 cubed, or 8. When I plug in a -5, I get 32, and when I plug in a -10, I get 1024. So then what happens when I go to graph all of these points? I have the point -10 comma 1024, which is off my chart. I have the point -5 comma 32, which is still way off my chart somewhere up here. I have the point -3 comma 8. There we go. I have the point -1 comma 2. I have the point 0 comma 1. And then I have the point 1 comma 1/2. 3 comma 0.125, just a little bit above 0. And then as my x's get bigger, what do you notice about your y values? Yeah, they get smaller and they approach 0, don't they? And so if you look at this graph, as my x's get bigger, it actually drops significantly, right? And so what we call this graph is exponential decay. We have exponential growth, where it shoots up really quick as x gets bigger, and we have exponential decay. So could we tell by just looking at the equation if it was going to be exponential growth versus exponential decay? Well, what do you notice about the equation? Well, you notice in example number 1, my base was a whole number that grew really quickly, exponential growth. But when my base is a fraction, right, or decimal, smaller than 1, then I have exponential decay. My graph is going to go down really quickly instead. So that's a quick, easy way to be able to figure out kind of what your graph is going to look like, if it's going to go up or if it's going to go down, exponential growth or decay. You notice that neither one of these graphs went below y equals 0, right? And every single one of these x values was able to be calculated. So I can keep going here into negative x's. I can keep going into positive x's. My graphs are just going to go really high up. And so my domain on any of these graphs is all real numbers, but my range kind of goes from 0, not including 0, and up, right? Because it doesn't ever touch 0 or go below 0. So kind of interesting on an exponential graph. Let's talk about in the next video what happens when I start to add or subtract numbers maybe next to my exponent or maybe behind my equation or in front of my equation. Either way, what do you think that does to my exponential growth or my exponential decay function?